All right. Okay, I'm going to go ahead and start here. Now, what we've got here is this is figure 1031 out of the book, and this is a simple, when I say the word simple, that's a relative term. It doesn't look simple, but it's a relatively simple memory interface for an 8086 system. That's there. And kind of go through here a little bit. It may be a little hard to read, especially if you watch this on the video, but as we look at this right here, and I may have to, because this is a little bit awkward to read, I may have to go back and forth. I'm going to actually go back to the original drawing right here in order to make it a little bit easier to read. Right there, and then I'll come back and we'll start right here, because I think this is a little easier to read right here. So as we look here, across the top, we've got D8 and D15. This is an 8086, so this is, it's got 16 address lines, D0 through D15. Now what's not shown on this drawing is the address data line demuxing circuits. Remember the address latch enable and those circuits to separate the address bus and the data bus from each other. So this particular drawing right here is after, wherever it's at, much further up in the chapter. That there, where we flash memory, it's much further up in the chapter. We talked about this to no end, right there, where we looked at the address decode. We're now getting to the address decoding way back at the beginning of the chapter. This chapter, we separated out the data lines from the. Actually, it was the previous chapter where we separated the. That's there. Now I'm not going to go through that again. But going back to this drawing where we're at here, let me get back to where I was at here. For those who just walked in, right here, I'm going to spend the hour analyzing. If I can get back to the circuit here, this circuit right here. So getting back to my earlier discussion, these buses right here, D8 through D15, D0 through D7, A1 through A15, A16, A17, A18, A19, A14, A15, A16, A17, those are all the address and data lines after we've separated them out with the address latch decoder and the gated latches. Remember, we used the gated latches in order to latch the address lines, so we kept them separate from the data lines. So this circuit here does not include that part of the memory interface. So this is just the address decoding portion of the memory face, right there. So as we look at this right here, we've got across here on the left, we've got all of our, these are our main, this is our data bus, and our data bus is relatively simple in the fact that we've got going to it right here. These are all right here. This is D0 through D7. It goes to this bus right here, and it goes to this bus right here, and then it also goes, as we go across here, it goes down to here to these two right here. So as we look at this right here, these memories are separated out. This is an 8-bit memory, and I'm going to go back to the other one simply because I can write on it here. Oh, that's not the right one. Right here. As we look at this right here, and I apologize for the fact that this is a little hard to read, and we want this to right here. So as we look at this right here, and I'm going to bring this down here. As we look at this line right here, this is D0, excuse me, D8, let me write this here, D8 through D15 right there. That's the upper 8 bits of the data bus. As we look at this, this line goes across here, goes down to this chip here, goes to this chip here, comes down here, and let's get this here, goes to this chip here. Actually, it does not go to this chip right here. I made a mistake there. Right there. Right here. As we take this line here, it goes across here. It comes down to this chip. Actually, it does go to this chip here. It goes across to this chip here. Comes down to this chip. And comes to this chip right here. So it goes to those 4 chips. These lines here, and I'm going to use a circle to show, these are all X's. So these X's right here represent the upper 8 bits of our data. Right there. D0 through D7 right here go to this chip here. We'll put a circle here. It goes to this chip here. And it comes down to this chip here. And it comes down to this chip here. So as we look at this circuit right here, these chips right down here, this chip right here, this chip here, this chip here, these chips here represent the lower 4 or 8 bits of the data. These chips here, those 4 chips here represent the upper 8 bits of the data. So when we look at this particular circuit, we're going to find that this chip here, right here, these 4 represent the lower 8 bits. So we've got 2 chips here that are going to have the same address as 2 here. So this chip here may have the same address as this one here. This chip here may have the same address as this here. This chip here may have the same address as this chip. This chip here may have the same address as this chip, because we want to address 2 of them at the same time, because this is a 16-bit data system right there. So whenever we address a memory location, we have to address 2 memory locations right there. Now, as we look at this right here, we're going to see that we've got our address lines right here. This is A1 through A15. I think that's right. I may have to go, let me go back and look at the, yeah, see A1 through A15 right there. And I'm going back here to make it a little easier to see. Right there, A0, where is A0 coming in here? I think that must be a typo. That is a frustrating thing to have happen. Yeah. No, it's not a typo. I take that back. And the reason it's not a typo is because this that there, and it's something I failed to mention, and it's a very important thing to mention. It's a gotcha that just got me, is that the 8086 really doesn't need to use A0 if it's going to be addressing data 16 bits at a time, because it's addressing 2 bytes each with each read and write. So A0 is not needed there, because A0 represents the odd and even. We're going to grab two bytes at the same time, so we don't need to use A0 right there. And let me kind of explain in more detail what I'm talking about there. You know, I'll come back to this page here. Add page right here. Is that, let's just look at, we've got, I'm going to just look at three bits of an address right there. 110111 right there. So this is going to address an 8-bit location right there. This is location 6. This is address 7 right there. These are 8 bits wide right there. The way we've got this configured is that we've got our data 16 bits wide. So this is location 110, this is 111. We address them both, we grab the data at the same time. We're going out and grabbing both this and this. Yes? Oh, okay. That's there. So, as a result, this A0 is not needed in this particular configuration. Is because we're grabbing the data 2 bytes at a time. So all we need is the 1-1, and that gets us both this location and this location. Gets us both locations at the same time. So A0 is not needed. Out there. And that's one of the reasons to go back and look at a actual schematic, is sometimes you forget something like that. So in this case, we don't have to use A0 when we're doing a 16-bit address, right? 16-bit data. If we're dealing with an 8088, we have to have A0 brought in there because that's only 8 bits wide. So now, getting back to this right here, let's go back to our circuit right there, right here. So as we look at this right here, this line here is A1 through A15 right there. So each one of these memory locations happens to be, we've got 15 address lines, right? 2 raised to the 15. Oh, I'm going to put it in scientific mode. 2 raised to the 15, which means they're 32K in size. So what does the right there, that doesn't make sense up there. Actually, A03, yeah, they each get 15 lines going to it. So 2 to the 15, so these should be and these are 128, so 128 divided by 8. That doesn't sound right. Yeah, 128 divided by 8 is 16K. That there. 16K. We've got A0 through A13 right there. This is supposed to be 64K EEPROM, so these should be 32K each. Yeah, 32K each. That makes sense. The amount of lines as we're looking at right there. Oh, hold on, take that back. No wonder I'm getting myself confused. As we look down here, our ROM only goes to A13, so it only has 14 lines going to it. So our ROM only has 14 lines going to it right there. So our ROM is 2 raised to the 14th. That's 16K. And going back and looking at our description here, this is 16K, but we've got 2 of those, so it's actually 16K by 8. So it's the way that they wrote this here is that what they don't say here is that, oh, no wonder I'm getting myself confused. I'm on the wrong drawing. Ever have a day that you just want to say go home and come back? That's there. I'm having that today. How did I get on the wrong page right here? Yeah, okay. Well, that doesn't change. All right. Somehow I got on the wrong page right there. So let's make sure we got this right. Yeah, everything's the same. Okay. Nothing's changed. So we've got, when we look at a ROM right here, we've got 4 ROMs that they're each 16K ROMs, right? As we went back and looked at our address, they're each 16K right there. But we've got, it's set up as, we've got, these two will make up 32K or 16K by 8, and this will make 16K by 8. So it tells us that we've got 64K bytes of EEPROM. That doesn't tell us the configuration. So our configuration is we've got 2 of these are talking together right there that make up a single 16-bit memory device, and then another 2 that make up a 16-bit memory device. So the way this is configured, and I said we're going to spend the entire hour analyzing this. I didn't say that we're going to spend the entire hour with me talking in circles. But as we look at this right here, what they're saying is we've got a 27128 right there, and this is a 16K by 8 right there is what that is. And we've got another 16K by 8, another 27128 right there. This is connected D0 through D7. This is D15 through D8 right there. So this makes up one bank. So this is a 16K by 8, or by 16K. There's a little button on the side here that I keep pressing accidentally right here. This is 16K by 16 bits, which is, when we look at bytes, that's actually 32K bits right there. Then we've got another bank right here that's the same, and that's another 16K by 16 right there. So as we go back and we look at our circuit right here, right there, as we look at the circuit right here, here's one 16K right here, and it goes back to these data lines we got across here. If we go across here, this data line is connected to these 4 chips right here. This one, this one, this one here. D0 through D7 is connected to these 4 right here. So as I said, this chip here forms a bank with this chip. This chip here forms a bank with this chip right there. So when we look at our decoding scheme, we haven't even started the decoding scheme. We're just looking at how the memory is connected right there. So we're bringing from here, A1 through A15 is connected to these data lines right here, these address lines right here. And they're all connected to the same address lines right there. They all are connected to those same address lines right there. We don't need A0 because our memory is 16 bits wide. If we wanted to look at A0, that means we can look at this chip versus this chip right here. Separate the high from the low order we can, but because we're using all 16 bits at one time, we don't need A0. So A0 in this particular case is not needed. It's not connected. It's probably used elsewhere in the circuit for looking at I/O addresses and things like that. But for the memory interface, we do not need A0 because our memory is 16 bits wide, right there. Now we get into the heart of this circuit is this part right here, and we're going to go through that in a little bit more detail. This is the memory decoding part right here. This is what tells us which of the 4 banks are selected. So when we look at this circuit, you have to look at this. There's 8 chips, but 2 of them are selected at the same time at all times. And the reason 2 are selected at all times is because they're 8 bits wide, and our database bus is 16 bits. So whenever we do a memory fetch with an 8086, we have to select 2 chips at the same time. So that's a very important thing when we're looking at a 16-bit microprocessor, is that our memory is addressed in 8-bit increments, but we're addressing 4 chips at the same time. If we had, for example, a 32-bit microprocessor, we would select 4 chips at the same time. And one chip would be connected from D0 to D7, the next one would be connected from D8 to D15, the next one would be D16 to D21, it'd be 23, and then D24 to D32. So you would select 4 chips at the same time. So in this particular case, we're looking at that right there. So, all right. Quick summary. We don't use A0. We use A1 through A15. Now, keep in mind that we're going to have some empty space in our memory map when we get this done, and we may not get this done during this time here. And the reason is that when we look at this here, A14 only goes to the static RAM, the static DRAM. Yeah, I keep hitting that there. Right there. I can't write in that there. But the A14 goes to these top chips. The bottom chips do not have an A14 connected to them. So whenever these bottom chips are used, then A14 is just ignored. It's not going to be looked at. And the reason is if we look at these top chips right here, they go through A14 to A15. We said that each one of these is what, an 8K by 8, right? 8K by 8, 8K by 8, 8K by 8, 8K by 8. That gets us, or was that right? 16K by 8. Excuse me, 16K by 8. These are 32K by 8s right there. So we have twice as much static RAM as we do EEPROM in this particular case, right there. So going back and looking at our circuit right here, as we look at this right here, we can see this goes A0 to A13, this goes A0 to A14. So A14, which in reality is A15, now I can really see the confusion showing up here, is that D0 is connected to, A1 is connected to A0 on these chips. So that completely was going to mess up your thinking here, there. And A15 here is connected to A14 here. A15 is not connected to A13 here at all, because there is no place for it. So as we look at this here, we can see the real confusions coming, is that coming off the microprocessor, we ignore A0. Why do we ignore A0? It's not needed. We're addressing memory 16 bits at a time, so we don't need to know odd or even. We're getting it both at the same time, so we do not need that. So since we do that, on the chips, we've got A0 set. We connect it to A1 coming out of the microprocessor. There. So as we analyze this, you can see there's all kinds of little tricks that people look at, and there's a reason for these. And I don't really think this book does a good job explaining that there. You leave some of that out, there. But then we've got some empty holes in our memory map when we come up with our memory map there. So, all right, as we look at this here, let's look at these 3 chips. We've got some chips here we haven't talked about. One of which is a 74LS128. Let's go ahead and pull up the data sheet for that. Right there. I think it's on my desktop. All right. I know I just downloaded it this morning to make sure I had it. All right. Now we go find it. There it is, LS120. Is that the right chip there? LS240, is that what it? LS240, okay, that's the right chip. All right, as we look at this particular chip right here, is that this is a 3-state output bus driver. All it is, so this is just a bus driver, is all this chip is right there. Octo line drivers right there, tri-state memory address decoder. So this does not change as long as it's selected right there. So going back and looking at our circuit right there, all we're doing is we're just buffering. And where's these lines coming from? A18 and 18, not A18 and A19. We're just buffering that there. Now this is where things get a little bit interesting, is that this is A18, A19, so this is A18 and A19. This is A18 and A19 going into this NAND gate right there. Also going into this NAND gate right here is the I/O memory NOT right there. So this NAND gate is only going to be selected when A18 and A19 are high. Right there. Let me go through where I got that from right there. So, right here, let me go back to my, right here. And you know what I'm going to do is let me do a new page right here, and let me there's no easy way of doing this right here. Edit okay, well let me just talk about what I wanted to do is view right here, is that there's no real easy way of just selecting this. Yeah. I wanted to just grab this right here just to there. This keyboard doesn't have a print screen up there. Okay. All right. Let's just kind of look at this here. A18 goes into A1. We can ignore this chip in terms of memory decoding. Let me just point that out right now. We can ignore this LS240. All it is a buffer. It has no bearing on the logic. So looking at the input of this 4-input NAND gate, or 3-input NAND gate, this is a 3-input NAND gate, which means the output will be low if and only if all 3 inputs are high going into this here. Pin 1 is tied to our line I/O memory NOT. So memory has to be selected for this output to be high. And we know that's to be the case. This is a memory interface. The A18 and A19 have to be high. So the output of this right here is A18 and A19 have to be high. Right there. So that there, and that will select this HC139. This happens to be an octal decoder, 2-input 2 to 4 decoder, which means that A16 and A17, which are the next 2 memory addresses we're looking at right there, A17 and A16, right there, if they're both low, then this output is going to be up there, and we're only looking at the upper 2. So let's kind of jump here and look at this right here. I'm going to go to the other one simply because I can write on it. Right here. Okay. As we look at this right here, this is our screen right there. This is a fresh one here. So as we look at this here, this is A18, A19 right there, right? I may have those reversed, but those are the two inputs there. This is memory, and as we recall, what is that line called? Memory IO not. Memory IO not. IO not. So this has to be high, this has to be high, this has to be high for this output to be low right there, right? So that tells me that as we look at this right here, this chip is only selected right here when A18 and A19 are high, right? Right there. The upper two bits of the address. Then this output is high when 16 and 17 are both high. This output is high when 17 is high and 16 are low. Right there. So this address is 1111. This is 1110 for the upper four bits right there. So as we look at that right there, and that goes to the chip select to this one here, this top one. And as we follow this across, it goes to the chip select on, it goes right here, it goes to this here. We follow this across here, and it goes to this run right here, right? So we can see where those lines are. And this is a tricky business right there. But this line here comes out of this here, goes to this chip select, is not connected to this one here, but it's connected to this one here. And that goes back to my early discussion that these two are selected at the same time. So these two devices right here, this one here and this one here, those two are selected when E is our upper address right there. E, X, 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 X right there. Those are selected. Those are selected when those particular addresses are that there. The other line coming across here is connected to this one here, right here. You see where it's connected there, and it's connected to this one here. So this is going to be selected when F, F, X, X right there. And this one is going to be selected on F, X, X right there. So that tells us that at the top of memory resides these two chips right here. Right there. Now, we have not looked at A15 right here. Right there. It's tied to this one right this here. But A15 is only selected when these are all high as well. So, but A15, this is coming through here. This is only looking at 18, 18, 19. So A15 is not used to decode this at all. A15 and 14 are used for these down here. You see, and these all have to be high here. You know, well, except for the fact that we're ignoring these two here, so that's okay. Right there. So as we look at this right here, and I lost my pin marks, didn't I? That's all right. Okay, let's just got to go through this here. You know, this is one of these lectures that actually A15. Oh, as I said, for those of you who came in late, I said I was going to probably get a phone call in the middle here. Oh, it didn't. It'll come through in a second.